potassium hydroxide is an inorganic compound with the formula KOH, commonly called caustic potash. Along with sodium hydroxide, this colorless solid is a prototypical strong base. It has many industrial and niche applications. Most applications exploit its reactivity toward acids and its corrosive nature. In 2005, an estimated 700,000 to 800,000 tons were produced. Approximately 100 times more NaOH than KOH is produced annually. KOH is noteworthy as the precursor to most soft and liquid soaps as well as numerous potassium-containing chemicals. Properties and structure: potassium hydroxide can be found in pure form by reacting sodium hydroxide with impure potassium. Potassium hydroxide is usually sold as translucent pellets, which will become tacky in air because KOH is hygroscopic. Consequently, KOH typically contains varying amounts of water. Its dissolution in water is strongly exothermic, meaning the process gives off significant heat. Concentrated aqueous solutions are sometimes called potassium lyes. Even at high temperatures, solid KOH does not dehydrate readily. Potassium hydroxide solutions with concentrations of approximately 0.5 to 2.0% are irritating when coming in contact with the skin, while concentrations higher than 2% are corrosive. Structure: at higher temperatures, solid KOH crystallizes in the NaCl crystal structure. The OH group is either rapidly or randomly disordered so that the O group is effectively a spherical anion of radius 1.53 a. At room temperature, the OH groups are ordered and the environment about the K+ centers is distorted, with K+ OH distances ranging from 2.69 to 3.15 a, depending on the orientation of the OH group. KOH forms a series of crystalline hydrates, namely the monohydrate CoH, 2O, the dihydrate CoH 2 hours, 2O, and the tetrahydrate CoH 4 hours, 2O. Solubility and desiccating properties: approximately 121 g of KOH will dissolve in 100 ml of water at room temperature compared with 100 g of NaOH in the same volume. Lower molecular weight alcohols such as methanol, ethanol, and propanols are also excellent solvents. Because of its high affinity for water, KOH serves as a desiccant in the laboratory. It is often used to dry basic solvents, especially amines and pyridines. Distillation of these basic liquids from a slurry of KOH yields the anhydrous reagent. Thermal stability: like NaOH, KOH exhibits high thermal stability. The gaseous species is dimeric. Because of its high stability and relatively low melting point, it is often melt cast as pellets or rods, forms that have low surface area and convenient handling properties. Reactions: as a base, KOH is highly basic, forming strongly alkaline solutions in water and other polar solvents. These solutions are capable of deprotonating many acids, even weak ones. In analytical chemistry, titrations using solutions of KOH are used to assay acids. As a nucleophile in organic chemistry, KOH, like NaOH, serves as a source of OH, a highly nucleophilic anion that attacks polar bonds in both inorganic and organic materials. In perhaps its most well-known reaction, aqueous KOH saponifies esters, KOH plus RCO2 or RCO2K plus Rho. When R is a long chain, the product is called a potassium soap. This reaction is manifested by the greasy feel that KOH gives when touched. Fats on the skin are rapidly converted to soap and glycerol. Molten KOH is used to displace halides and other leaving groups. The reaction is especially useful for aromatic reagents to give the corresponding phenols. Reactions with inorganic compounds: complementary to its reactivity toward acids, KOH attacks oxides. Thus, CO2 is attacked by KOH to give soluble potassium silicates. KOH reacts with carbon dioxide to give bicarbonate, KOH plus CO2 or KHCO3, manufacture. Historically, KOH was made by adding potassium carbonate to a strong solution of calcium hydroxide, leading to a metathesis reaction which caused calcium carbonate to precipitate, leaving potassium hydroxide in solution, Ca, OH, 2 plus K2CO3 a Carco3 plus 2 KOH. Filtering off the precipitated calcium carbonate and boiling down the solution gives potassium hydroxide. It was the most important method of producing potassium hydroxide until the late 19th century, when it was largely replaced by the current method of electrolysis of potassium chloride solutions. The method is analogous to the manufacture of sodium hydroxide, 2KCl plus 2 hours 2OA2 KOH plus Cl2 plus H2. Hydrogen gas forms as a byproduct on the cathode. Concurrently, an anodic oxidation of the chloride ion takes place, forming chlorine gas as a byproduct. Separation of the anodic and cathodic spaces in the electrolysis cell is essential for this process. Uses: KOH and NaO can be used interchangeably for a number of applications, although in industry, NaO is preferred because of its lower cost. Precursor to other potassium compounds, many potassium salts are prepared by neutralization reactions involving KOH. The potassium salts of carbonate, cyanide, permanganate, phosphate, and various silicates are prepared by treating either the oxides or the acids with KOH. The high solubility of potassium phosphate is desirable in fertilizers. Manufacture of biodiesel, although more expensive than using sodium hydroxide, KOH works well in the manufacture of biodiesel by transesterification of the triglycerides in vegetable oil. Glycerin from potassium hydroxide processed biodiesel is useful as an inexpensive food supplement for livestock, once the toxic methanol is removed. Manufacture of soft soaps, the saponification of fats with KOH is used to prepare the corresponding potassium soaps, which are softer than the more common sodium hydroxide-derived soaps. Because of their softness and greater solubility, potassium soaps require less water to liquefy, and can thus contain more cleaning agent than liquefied sodium soaps. As an electrolyte, aqueous potassium hydroxide is employed as the electrolyte in alkaline batteries based on nickel-cadmium, nickel-hydrogen, and manganese dioxide zinc. Potassium hydroxide is preferred over sodium hydroxide because its solutions are more conductive. The nickel metal hydride batteries in the Toyota Prius use a mixture of potassium hydroxide and sodium hydroxide. Nickel-iron batteries also use potassium hydroxide electrolyte. Niche applications, like sodium hydroxide, potassium hydroxide attracts numerous specialized applications, virtually all of which rely on its properties as a strong chemical base with its consequent ability to degrade many materials. For example, in a process commonly referred to as chemical cremation, or racemation, potassium hydroxide hastens the decomposition of soft tissues, both animal and human, to leave behind only the bones and other hard tissues. Entomologists wishing to study the fine structure of insect anatomy may use a 10% aqueous solution of KOH to apply this process. In chemical synthesis, the choice between the use of KOH and the use of sodium hydroxide, NaO, is guided by the solubility of the resulting salt. The corrosive properties of potassium hydroxide make it a useful ingredient in agents and preparations that clean and disinfect surfaces and materials that can themselves resist corrosion by KOH. Potassium hydroxide is often the main active ingredient in chemical cuticle removers used in manicure treatments. Because aggressive bases like KOH damage the cuticle of the hair shaft, potassium hydroxide is used to chemically assist the removal of hair from animal hides. The hides are soaked for several hours in a solution of KOH and water to prepare them for the unhairing stage of the tanning process. This same effect is also used to weaken human hair in preparation for shaving. Pre-shave products and some shave creams contain potassium hydroxide to force open the hair cuticle and to act as a hygroscopic agent to attract and force water into the hair shaft, causing further damage to the hair. In this weakened state, the hair is more easily cut by a razor blade. Potassium hydroxide is used to identify some species of fungi. A 3.5% aqueous solution of KOH is applied to the flesh of a mushroom and the researcher notes whether or not the color of the flesh changes. Certain species of gilled mushrooms, bolides, polypores, and lichens are identified based on this color change reaction. Petroleum refineries, Potassium hydroxide is also used in petroleum and natural gas refining for removal of organic acids and sulfur compounds. See also, soda-lime, references. External links, New Scientist article DN 10104, MSDS from Baker, CDC, NIOSH Pocket Guide to Chemical Hazards.